Hello, friends. Welcome back to Webronaq. Quick question to start with. How do you think a computer stores the number 0.5? We all know computers only understand zeros and ones, so whole numbers like 5 or 12 are easy enough. There's a clear way to break them down into binary. But the moment you add a decimal point, things get interesting. In this video, we're going to crack open exactly how fractions are stored in binary. By the end, you'll be able to look at any binary fraction and read it like a regular number. Let's get into it. All right, before we jump into fractions, let's quickly remind ourselves how binary works for normal whole numbers. Take this number, 1011 in binary. Each digit sits in a specific position, and each position has a value. Starting from the right, the place values go up in powers of 2. So 1, then 2, then 4, then 8, and so on. Each time you move one step to the left, the value doubles. So to read this number, we just add up the place values where there's a 1. We've got an 8, no 4, a 2, and a 1. Add them up. 8 plus 2 plus 1 equals 11. That's how 1011 in binary becomes 11 in decimal. Now here's where it gets interesting. What happens to these place values when we move to the right of the number? That's exactly where fractions come in. Now look at this. Here's the big idea. The place value system doesn't just stop at the binary point. It keeps going. On the left side of the point, every step doubles the value. 1, 2, 4, 8, and so on. But on the right side, it's the opposite. Every step halves the value. So the first position right after the point is 1/2. The next one is 1/4. The one after that is 1/8. And it keeps going. 1/16, 1/32, smaller and smaller. If you've ever zoomed into a photo in Photoshop or any image app, you'll notice the zoom levels often go 100%, 50%, 25%, 12.5%. Each one is half of the previous. That's the same pattern happening here, just with binary place values. So in binary, the number to the left of the point is the whole part, and the digits to the right of the point are just fractions being added on. Let me show you exactly how to read one. All right, let's actually read a binary fraction. Take this number, 101.101. The rule is simple. We just look at every digit that's a 1, multiply it by its place value, and add them all up. The zeros we can skip, because anything times 0 is 0. So starting from the left, we've got a 1 in the 4's place. That gives us 4. Skip the next 0, then a 1 in the 1's place. That's 1. Now we cross the binary point. The next one is in the 1/2 place, so that's 0.5. Skip the next 0, and the last one is in the 1/8 place, which is 0.125. Add them all up, 4 plus 1 plus 0.5 plus 0.125, and we get 5.625. That's it. That's the whole trick. 101.101 in binary is just 5.625 in decimal. Pretty simple once you see the pattern, right? Now let's flip it around. What if we want to go the other way? Start with a decimal fraction and convert it into binary. Okay, so going from binary to decimal was pretty straightforward. Now let's reverse it. Say we have the decimal number 0.625 and we want to convert it into binary. How do we do that? There's a neat little trick. It's called the multiply by 2 method. Here's how it works. Take the fractional part and multiply it by 2. Look at the result. If the whole number part is 1, write down a 1. If it's 0, write down a 0. Then take whatever fraction is left over and repeat. Let me walk you through it. We start with 0.625. Multiply by 2, that gives us 1.25. The whole number part is 1, so our first bit is 1. We drop the 1 and keep the 0.25. Now multiply 0.25 by 2. We get 0.50. The whole number part is 0, so our next bit is 0. We keep the 0.50. Multiply 0.50 by 2, we get 1.00 exactly. The whole number part is 1, so our next bit is 1. And since there's nothing left after the decimal, we stop here. Read the bits in the order we got them. 1, 0, 1. So 0.625 in decimal is just 0.101 in binary. Done. But here's the thing. This worked out really cleanly because 0.625 happens to be a nice fraction. What if we try a number that isn't so cooperative?
All right, let's try something simple. Let's convert 0.1, yes, just plain old 0.1, into binary. You'd think this would be easy, right? It's such a small, friendly-looking number. Watch what happens. Multiply 0.1 by 2, we get 0.2, so the bit is 0. Multiply 0.2 by 2, that's 0.4, another 0. Multiply 0.4 by 2, 0.8, still a 0. Multiply 0.8 by 2, now we get 1.6, so the bit is 1. We drop the 1, keep 0.6. Multiply 0.6 by 2, 1.2, another 1. Drop the 1, keep 0.2. And wait, we've already seen 0.2 before, back in step 2. So from here, the whole pattern just starts repeating itself, forever. So 0.1 in binary is actually 0.0001100110011, and those last 4 digits, 0011, just keep repeating endlessly. There's no clean stopping point. Now, here's the problem. A computer doesn't have infinite memory. It can only store a fixed number of bits, usually 32 or 64. So at some point, it has to chop off the rest of the digits. That tiny chop is exactly why, in many programming languages, when you add 0.1 plus 0.2, you sometimes get a weird answer, like 0.300000000000000000004. It's not a bug. It's just that 0.1 was never exactly 0.1 inside the computer to begin with. We'll go much deeper into this in our upcoming videos on floating point notation and truncation errors. For now, just remember, not every decimal fits perfectly into binary, and that has real consequences. All right, let's quickly tie it all together. First, in binary, place values don't stop at the binary point. They keep going on the right side too, just halving each step instead of doubling. Second, to convert a decimal fraction into binary, we use the multiply by 2 trick. Multiply, write down the bit, drop the whole part, repeat. And third, not every decimal converts cleanly. Some, like 0.1, repeat forever in binary, which means the computer has to cut them off at some point. And that small cutoff is the reason you sometimes see those strange floating point errors in code. In the next video, we're going to look at how computers store negative numbers using something called 2's complement notation. It's a clever little trick, and once you see it, it's actually really satisfying. If this video helped you understand binary fractions better, hit that like button, share it with a friend who's learning programming, and subscribe to Webronaq for more clear, simple breakdowns of computer science concepts. See you in the next one.